Hello, and welcome to another edition of Amptitudes. My name is Kevin Treader, product marketer with Microchip technology. In past episodes, we focused a lot of attention on precision devices, such as zero-drift op-amps and instrumentation amplifiers. One of the key benefits of the zero-drift architecture is extremely low drift over temperature. For example, the MCP 6V61 zero-drift op-amp specifies a maximum drift of 15 nanovolts per degree C, which is over 100 times better than that of a general-purpose amplifier, and that's being conservative. But to realize the performance benefits of such devices, high-precision analog designs must also pay attention to the rest of the circuitry and follow sound PCB layout techniques. This video will focus on the effects of temperature transients and how to minimize the adverse effects. When two dissimilar metals come into contact and that junction is heated, a voltage shift will occur. This is commonly known as the Seebeck effect and is the basis of how thermocouples are used to measure temperature. However, there are lots of unintended thermal junctions on a typical printed circuit board design, such as components soldered to the copper pad, vias, jumpers, and so forth. Let's take a look at how these thermal junctions can affect the accuracy of a precision circuit. This illustration shows a typical copper trace with a surface mount resistor. For this case, let's assume the temperature gradient is parallel to the trace. The thermal junction voltage effect is roughly proportional to the difference in temperature between the ends of the resistor. This effect is a function of resistor size, the types of metals in contact, and the severity of the temperature gradient. In this example, we assume a temperature gradient of 0.3 degrees C across the resistor, which results in a temperature drift around 1 microvolt per degree C change, much higher than the drift of a typical zero-drift amplifier. Now let's examine a case in which the temperature gradient is perpendicular to the trace, as opposed to parallel, as shown in the previous case. Since the copper traces and the resistor ends are all at the same temperature, there is no error due to the thermal junctions. Now that we understand how thermal junctions work and the errors associated with them, how can we minimize these errors? The key is to understand the effects of thermal junctions on a given circuit and proper PCB layout. Let's look at a simple non-inverting gain stage. In this example, the layout of the resistors are placed for ease of routing, but provide very poor cancellation of thermal-related errors, as the accuracy will be impacted by gradients in both the X and Y direction. This next layout example is better, as it removes any errors associated with thermal gradients in the Y direction, but is still impacted by gradients in the X direction. In this third layout example, R3 is rotated 180 degrees and is in vertical alignment with the other two resistors. This helps to minimize the thermal junction effects in the X direction. Now I realize I ran through these examples quite quickly. If you would like more information on this topic, including the actual circuit analysis that was used to draw these conclusions, I strongly recommend Microchip's application note AN1258. I also recommend Microchip's master's class called High Precision Analog Applications Using Amplifiers, which can be found on Microchip's YouTube channel. Thank you for joining me for this edition of Amptitudes. I'll see you next time.